All right, welcome everybody to the last official, I guess, session of the workshop. Much looking thoughtful TDEs in theoretical part. And the first speaker in the morning is going to be Brenna Mockler, and she's going to be telling us about data disruption events on supermassive black hole binaries.
Or not. So yeah, thank you so much to the organizers. I've had a great time here. I've learned so much, had great discussions. Look forward to continuing those discussions after the workshop this year. So today I'm going to talk about work I've done in collaboration with quite a few people, but in particular Denise Melchor, a student at UCLA. And this is work on Untitled Chapter events for supermassive black hole binary. So this is an artist's rendition of a supermassive black hole binary. You can imagine if the TDE went off, and maybe we could keep this. But before I go in, TDE is paused. Oh, okay. All right. There we go. Before I go into more detail about binaries, I do want to emphasize that we actually have learned a lot about single supermassive black hole populations from TDEs. So just emphasizing some of the stuff Suvi talked about yesterday, we're already probing the black hole mass function with TDEs. We see in the plot on the left there, the hill capture predicted by people including Mike Kesman in 2012. And then on the right here, we're actually, you can see how we're probing, we're both constraining and extending the supermassive black hole function to lower masses compared to other previous observational efforts, which I think is really exciting, even though we still have many theoretical questions, of course. But then obviously we don't expect all supermassive black holes to be singles. Galaxies merge. Eventually those supermassive black holes will form binaries. This is the galaxy merger rate, major merger rate as a function of redshift, both for illustrious, those are the lines, and then the scatter points are for different observations, and they're relatively consistent, particularly at lower Z, there's smaller error bars. And basically what I want you to take away from this is that the merger rate at redshift less than 2 or so is somewhere between a few percent to tens of percent. So depending on what you believe for the time scale it takes these binaries to harden, we might expect a few percent, 10% of supermassive black holes to be in binaries. Of course, that was a major merger rate. You can also look at the minor merger rate. This plot is from the Lester simulations again, where you can see that the minor merger rate they get is a few to maybe even 10 times higher, but for 10 to 1 or 10 to 1 or 100 to 1 mass ratios, we're getting maybe 2 to 6 times higher than major mergers, which is actually consistent with low Z observations. It's harder to throw this out higher Z. And so can we actually learn something about supermassive black hole demographics from TDEs? The nice thing about tidal disruption events is they're going to probe this intermediate regime between where we expect to, or where we can currently directly resolve dual AGN or measure the effects on the broadline region of the AGN, and where we will eventually hopefully be getting gravitational wave emission from LISA. And so we find that there are strong dynamical perturbations that are increasing TDE rates when the black holes are of order the sphere of influence of each other's separation. So a fraction of a parsec to a few parsecs. And so there are many ways that you can increase the rates of TDEs. Some of those are just related to changes, well, all related to changing the potential, but without even three-body interactions, you can get different non-spherical potentials that increase the rates. But at these this hard binary stage, the thing that is going to be most dominant is these three-body interactions that can increase stellar eccentricities. And then because of the increased eccentricities, dramatically increase the rates of both single and repeated events. My computer's a bit slow today. Yeah, so some of the big picture questions that I want to try to address in this talk are, first of all, when do these processes affect rates? Can these bursts of TDEs actually help us find supermassive black hole binaries? And what other phenomena can we, sorry. Actually just got a new computer, but I haven't set it up yet. But yeah, and what other phenomena can we expect to find from this? For example, repeated TDEs or potentially Emery events. So when I talk about three-body interactions, what am I talking about? Well, you can get coherent orbital excitations like the quasi-Lido mechanism. You can also get chaotic scatterings where just a single orbital passage, a strong scattering event can send the star towards the black hole on a very high eccentricity orbit. And this has been studied in detail in the past. Like preemptively.
Is it the Zoom that is delayed? Or
I think it's not, it's not showing up on my computer either. It's slightly even more delayed on the Zoom. But I wasn't noticing it when I was just going through the slides earlier, so it must be.
You want to go? Oh, there you go.
Okay, yeah. Maybe if it happens again. So today I'm going to focus on the coherent orbital excitations. And the reason for that is because, as it turns out, these are more effective around the smaller supermassive black hole binary. And there are multiple reasons why we think that black hole will be more exciting, both for probing hidden supermassive black hole binaries and for producing repeated tidal disruption events. Yeah, and so very brief comparison to other processes. We generally think of rates from two-body relaxation, right? This is a random out process. So the average velocity cancels out. The changes are coming from the variance building up in angular momentum and energy space. And many people have worked on this and shown you can estimate the loss cone of TDEs or of stars to tidal disruption events, depending on the potential. Mike has worked a lot on this, and what people find is that you get a critical radius where you're sourcing most of your TDEs that for the black holes in the 10 to the 6th solar mass range or so is actually of order of the sphere of influence. And so that's where most of the tidal disruption events are coming from. For this before, this is a Metzger paper. Hopefully Mike will maybe talk later about a more recent paper, including GR effects. Odelia Tabol is a student who recently had a paper thinking about including strong scattering events and super dense stellar crusts. So there's a lot of interesting work being done on this. But then in comparison, what's happening with quasi-Lido? Well, these are coherent excitations. The perturbations are building up very quickly, so we don't have this random walk n to the 1/2 behavior. And so you're basically exchanging angular momentum between the two orbits, but that's really only noticeable for the inner orbit of the star and the black hole. And it's not significantly changing the binary's orbit. But what that leads to is these very high eccentricity excitations. So the plot on the right has 1 minus the eccentricity versus time in years. And you can see that the eccentricities you're getting to are like 0.9999, certainly high enough to produce disruption, probably plunges in this case. But an important thing to note is you can get source radii much less than the sphere of influence, because now what's determining where most of the stars are coming from is the separation of the binary. And in fact, most of the quasi-Lido oscillations are happening on smaller scales within a sort of hierarchical radius limit out within the chaotic regime, or within the radius where you'd have chaotic scatterings. So this has been studied in detail, but most of the work has been done. Well, quasi-Lido has been studied in detail since the 60s, but most of the work for supermassive black hole binaries and TDE rates has been focusing on the larger black hole. And this makes sense just in that there are more stars around that black hole, so you'd expect to be able to get more disruptions. But what people have found is that most of the disruptions end up coming from these chaotic orbital scatterings, and that quasi-Lido oscillations are suppressed. That's what the plot in the left is showing. So we have the angular momentum, the z component of the angular momentum versus radius. You have your initial stellar distribution. You have this cosi wedge where you would expect most of the disruptions to be coming from quasi-Lido oscillations. But then all of these dots are where the actual TDEs are coming from. And most of them are coming from chaotic scatterings. And so this actually lowers your rate a little bit, but I think by a factor of 2 or so. But what's really important in this result is that most of the disruptions aren't coming from the quasi-Lido oscillations. And this makes sense if you actually compare the dynamical timescales. So this is time versus semi-major axis for relevant parameter space of a black hole, a disrupting black hole of 10 to the 7, a perturbing black hole of 10 to the 6. And so the timescale is a proxy for the amount of change in angular momentum of the orbit. And you can see that through the relevant parameter space, GR precession and stellar cusp precession dominate. And this is again what was found in this previous work. They are getting disruptions, but it's through these chaotic scatterings, which is going to be a border the orbit of the binary, right? Not at some smaller radius, because they need to actually scatter off the orbit. However, if you change the ratio and you instead have the disrupting black hole be the smaller black hole, we would expect some cluster of stars to remain around both of them. Then the Kozai-Lidov timescale actually is less than both the GR precession and the stellar cusp timescale for much of the relevant parameter space, and we would expect to see this in these interesting oscillatory eccentricity behavior.
By stellar cusp,
What? Sorry.
by stellar cusp, you mean change of potential compared to just the black hole, to the stars now?
Yeah, I mean the Newtonian precession from the yeah. So yeah, I should have clarified that. Thank you. Yeah. So basically, just to give a little bit more detail, both of those processes are going to cause the resonant angle in the Kozai-Lidov process to precess, since you can move it out of the parts of parameter space. And I'll talk about this more later, where you're expecting these high eccentricity oscillations. And I think this just shows really clearly the issue where you have the perturbing black hole versus the disrupting black hole. And in color, I'm plotting the number of stars that are susceptible to these Kozai oscillations, or analytically calculating it. Where the 1-to-1 line is here, it's not through the middle of the plot, just to emphasize that the majority of the disruption, or majority of the stars that are susceptible to this, we would expect to come from around the smaller black hole than around the larger black hole down here, where these Kozai-Lidov oscillations are suppressed by, in this case, precession from GR and stellar cusp. And so this has been studied, this was pointed out by Lee et al. 2015. And so they did a small study showing that for one setup, they found they studied Kozai-Lidov around the smaller black hole. They found that the oscillations weren't suppressed. A similar work has been done for intermediate mass black holes by Giacomo Fragione, if I'm pronouncing his last name right. He's a collaborator, so I really should. Both of them found that this was promising, that there still seemed to be Kozai-Lidov oscillations. And so we went further here and explored more parameter space that we thought would be particularly relevant for tidal disruption events. And a little aside, when I say eccentric Kozai-Lidov instead of Kozai-Lidov, I just mean the octuple level expansions. This has been developed a lot by Sven Arnauz. And the difference here is that you're not assuming the Z component of the angular momentum is constant. So it's actually accurate for eccentric supermassive black hole binaries, which is probably more realistic when the binaries come in, unless I guess there's a lot of gas. And importantly, for tidal disruption events, you can reach much higher eccentricities than you can with the lower level expansions. You'd expect many more TDEs from this process.
Just understanding this exercise, you only consider three-body interactions?
We do, well, so we do also include depending, I'll go into more detail this later, but we include the effect of GR precession in these simulations. We actually don't include the effect of stellar cusp, but we compare with the work by Gonsier and find that we get the same result.
Because in some regions of that parameter space, the number of stars,
Sorry. Yeah. So, sorry, so what are you saying?
I'm just wondering at what stage you actually need to worry out the presence of so many stars.
Exactly. So the second project that I'll be talking about is including with this that Denise Melchor led, is including the effect of two-body relaxation. And we show that while it doesn't dramatically affect the overall rates, we do see some changes, and in particular, we see that we're able to get some repeated tidal disruption events. Basically, even though in that case, the two-body relaxation time scale, I'll talk about this more later, but is small, the little kicks, individual kicks per orbit in angular momentum space occasionally can cause diffusion in that resonant angle that I was talking about. And so you actually get even more stars that are pushed into a regime where they're able to excite their eccentricities. It doesn't dramatically change the probabilities, but yeah, that's what it will get to. That's next point. So yes. Okay, but for finding supermassive black hole binaries with TDEs, why do we care about the smaller black hole? Well, the simplest thing is just that TDEs around the larger black hole are going to be difficult to tell apart from disruptions around a single black hole. So if we can improve and constrain the mass measurements from TDE light curves and spectra, then the measurements should be consistent approximately with galaxy scaling relations. I mean, there's uncertainties about how those hold up during merger processes, but we expect them to be more consistent with the larger black, the scaling relations to be consistent with the larger black hole than the smaller black hole if these mass ratios are 10 or more. And so if you look at the literature that is trying to estimate black hole masses using TDE models, what we find is that most of them, with the exception of Ryan's new model, have their timescales limited by the fallback rate. And so what I mean by this is it's possible to get longer lived light curves, but it's much more difficult to get shorter lived light curves than what you would expect from the fallback rate. So it sort of sets the minimum timescale of the light curve evolution. And so the fallback rate, we know, as other people have pointed out, is going to increase with the mass of the black hole. This is the fallback rate versus time in days as you go from smaller to larger black holes, so 10 to the 5 to 10 to the 8 in this case, and you can dramatically see the increase in the time scales. And so if we see light curves that are too short to be powered by disruptions from a larger black hole, and they're not repeated TDEs, which we talked about earlier, because but we would see the repetitions in that case. If they're too short to be powered by disruptions from the larger black hole, then they're candidates for hosting a second supermassive black hole in that system. And so what would we expect this to look like? This is the M sigma relation for the relevant mass range. So points in black and gray are calculated from AGN. I use my model here to calculate measurements for TDEs in red, and I need to update it with just recently been a lot more velocity dispersion measurements. So I just need to fit those events. They seem mostly consistent, but this is the parameter space down here where we would expect to find these hidden supermassive black hole binaries. So if we're starting to populate this region, especially as we hopefully improve our constraints in the black hole masses from different light curve and spectral measurements, then we might be seeing a population of these hidden supermassive black hole binaries. And of course, in the most extreme case, if you see a TDE in a galaxy that really appears too massive to host most disruptions, or if you see a population, so it's harder to explain with one-off very weird stars, then that would be a very good candidate for a supermassive black hole binary. And I think Eric Coughlin mentioned this in his 2018 paper as well, probably others. So I'll jump right into our results here. So the first set of simulations, we didn't include the two-body relaxation kicks, but we set up a series of different binary supermassive black hole simulations with nuclear star clusters around them, looking at the three-body interactions. These here that I'm plotting are for different disrupting black hole masses, but the same mass ratio and the same stellar density profile. Those are other parameters we varied. You can see again, I'm plotting 1 minus eccentricity versus semi-major axis. And this is the maximum eccentricity of each of the stars. And we see this clustering down here below these dashed lines, and those are tidal disruption events, or in the most extreme cases, plunges, where we're setting our limit here for the critical radius to include partial disruption, so including beta down to 0.5, which is around where it seems like hydro simulations are finding noticeable amounts of mass fallback. So we find all of these tidal disruption events. What does this actually mean for the rates? Well, here's a time-dependent rate as a function. So the TDE rate versus time for those same simulations I was plotting before. And so we see the expected burst. And the burst is just caught, so you get this high rate of TDEs, and eventually the region of parameter space that's sensitive to this is depleted. And I'll show that that's one of the reasons we get an extension with two-body relaxation, but it's depleted, and so then you have this drop off. But importantly, the thing I want you to notice here is if you look at the observed rates, various, I think this is mostly from Van Belzen's 2020 paper, but comparable to other observational rates. They're all kind of between 10 to the minus 4, 10 to the minus 5. We get higher rates for timescales of here tends to really up to over 100 million years, depending on the primary black hole mass. So we would expect these to be observable during their bursting phase. And I don't actually have in this particular plot, just didn't want to make it too messy, I don't have the theoretical rates, but of course, if we expect the two-body relaxation rate to decrease with increasing black hole mass, then you can expect this to be much more prominent at the higher disruption, higher black hole mass disruptions. And then one thing I want to do is, before I go on to the second part of this, is compare the number of tidal disruption events between the two black holes in the system. This is TDEs from the small black hole. There's scatter here, or there's from changing the stellar cusp, because if you have more stars close to the black hole, you're able to get more of these disruptions. But then also, depending on what you assume for the stability condition. So if you assume that as soon as a star's apocenter moves at all outside the Hills radius, it is scattered, then you get a lower limit. And if you assume that it's able to then get disrupted before you would expect that scattering to occur, then you can have a higher limit. And there's other papers I can point people towards that look at that in more detail.
Can you say what about how you actually initialize all of this?
Yeah, so we choose, so we have different stellar density cusps, so we're choosing the radius randomly based on the density profile. We also are choosing the different orbital parameters essentially randomly. I think we have a thermal distribution for eccentricity, so that's not a Gaussian centered on 0.5, but rather 2/3. But then it's basically just like a Monte Carlo, like choosing them randomly in each simulation case and then letting the system evolve. Other than the density profile, which is, has the prior based on different cusp profiles. And so if we compare the number of TDEs from the smaller black hole to what not our simulations, other simulations have predicted from chaotic orbital crossings around the larger black hole, you actually get pretty similar results for mass ratios of 1 to 10. The fact that our upper limit matches so closely with theirs is kind of a fluke. It's just because I chose a mass ratio of 10. So if we chose a different mass ratio, it wouldn't be quite on top of each other like that. But hopefully this emphasizes that in these systems, we would expect disruptions around both black holes. We should consider the dynamics of the stars around both the black holes. And that's very exciting for the potential of using TDEs to actually find hidden supermassive black hole binaries. And the reason that they're similar is even though there are so many more stars around the larger black hole, just as I was talking about earlier, the strength of these EKL precessions is so much stronger on the smaller black hole. I mean, there's a much bigger black hole that's perturbing it, that you're able to disrupt a much larger fraction of the stars. And then just a quick comparison, this isn't an exact comparison, but with two-body relaxation, obviously that's a more continuous process, but if you look over a similar time scale, I think I chose 10 to the 8 years here, you can see that you cross rates around 10, or you cross number of disruptions around 10 to the 6 or so, which is also kind of what you see in the, for that time scale in the time-dependent rate plots. So for these larger mass black holes, you're getting more disruptions on relatively long 100 million year time scales. Okay, so for my last part of the talk, I think we started a bit late, so I have like 5-10 minutes. Okay. So I'm going to talk about repeated TDEs. And so just to remind people why we think it's difficult to get repeated TDEs from two-body relaxation, simple argument. If you're sourcing your TDEs from the sphere of influence, that's size scale is 1 parsec-ish, that's periods of 10 to the 5 years. If instead you use EKL, I mentioned earlier that the separation is, the time scale, the critical radius is dependent on the binary separation. So in general, for most of our TDEs, it's less than 0.1 or so the binary separation. So if you were separated by, if you had a semi-major axis of the binaries of order the sphere of influence, then you do a bit better. You get periods of 3,000 years. That's still not human lifetime scales. On the other hand, if you include two-body relaxation, what I was talking about before is you're increasing the parameter space susceptible to EKL, and so you're actually able to get more disruptions at smaller radii, because you can have smaller or less dramatic EKL precession that moves the star slightly and closer to the black hole, and then you can have more two-body relaxation at that point that moves it closer, and you kind of go back and forth between those two. And I will show you some plots of that. And what we find is that we can get periods less than a year. Back to having issues. That was better. Yeah.
The suspense.
Oh, the suspense. Yeah, I know. I wish I had stopped on like a complicated plot to explain or something. That would be more useful instead of just like an overview. Try one more time. Oh, okay. Yeah, there we go. So the reason that people hadn't looked at this in the past is because if you just naively plot the two-body relaxation timescale and eccentric cosi of timescale in a similar way that I was showing earlier, you find two-body relaxation is much longer. But this is plotting the two-body relaxation timescale, often considered is the diffusion in energy, which is more comparable to a change in the circular angular momentum of the orbit. And so if you instead look at the per orbit changes in angular momentum, you get something that's a little bit better. Here, these two timescales are more comparable over this parameter space, but still eccentric cosi seems clearly dominant. And in fact, we find it is. However, those little kicks are enough to move you into different parameter spaces, into different resonant angles, where suddenly cosi is more effective. And so even though they're relatively small compared to the effects of cosi at a given radius, because it's eccentric cosi is a chaotic process, you can get these really long, big changes in the longer term behavior. So I think this plot shows that a bit better. It's a bit complicated, so I'm just highlighting the bottom one first. And this is showing the changes in the resonant angles. This is the argument of pericenter. And so there's three different lines on here. The gray and the blue just kind of look like big squiggles. And that's because both of those two simulations have EKL included. And they're showing that you get these giant oscillations in the resonant angle. But if you remove EKL and just plot the evolution of the resonant angle here with GR precession and two-body relaxation, then the overall trend is what you'd expect from GR precession, which is to say that the angle is smoothly changing. But you get this stochastic behavior on top of it from two-body relaxation, and these little changes are changing the resonant angle. And so it's like moving it into different zones of where cosi might be effective or might not be effective. And so even though you can't see those in the big, in the blue and gray lines, they end up being very important. And so the blue lines are when you include all these three processes, EKL, GR, and two-body relaxation. And the gray is not including two-body relaxation. And so if you now look at the top plot, that's showing the both the separation of the semi-major axis of the star and its pericenter. And it's kind of hard to see, but the gray line, squiggly lines in the background, that's the pericenter of a star undergoing these cosi of oscillations without two-body relaxation. So it is undergoing these oscillations, but the pericenter is maybe only changing by a factor of a few. When we include two-body relaxation, what we find is at first qualitatively similar behavior. The oscillations are similar in size. And then all of a sudden, two-body relaxation, at actually the same time that the semi-major axis is changing in this case, is moving the star into a part of parameter space where suddenly you're getting these much larger oscillations. And this particular plot is actually for emeries, so it ends in a GW source, but you could imagine for a star, what you get is a tidal disruption event. And so the next couple plots, I'm going to show you this for a case where we get a repeated TDE where we otherwise would not. So this is a similar plot, but now we have the distances on the top. So the pericenter radius, the semi-major axis. This is without two-body relaxation, just EKL. You see the nice oscillations in pericenter radius and in the bottom showing inclination. If we include two-body relaxation, then in this case, actually at first, those oscillations are suppressed. And so you're not getting very much oscillatory behavior in the pairs or in the eccentricity. And then suddenly you move into a part of parameter space where you can get these oscillations. And eventually both the semi-major axis actually starts decreasing near the end, kind of in coordination with the eccentricity, and you finally get a tidal disruption event at smaller radii than where the star started. And in this particular case, it would be a repeated TDE on human timescales. And so we find that not for a huge number, but for a subset of the tidal disruption events, and this is in Denise Melchor's paper, she finds that she does get these repeated TDEs. And so quick, kind of before I show you the specific repeated TD demographics, I want to kind of answer your earlier question was what does this affect? How does this affect the total rates? This is another plot from her paper. So the overplotted kind of bright blue and bright purple lines are the rates that she gets. The kind of slightly more darker hatched lines in the background are rates that I got for the same setups. And so qualitatively pretty similar, but my rates have slightly higher peaks and they drop off slightly more quickly. So she finds this lower peak. So that behavior in the last plot where you're seeing there's suppression in the oscillations, that's true in many of these cases, but then eventually most of those stars will actually end up getting excited. And so they will get disrupted just on slightly longer timescales. But in principle, that's actually better observationally, right? Because the rates are still higher than the observed rates. And they'd be, well, depends on how often you think you have these close supermassive black hole binaries, and they'd be longer lived.
What is alpha in this plot, like two colors?
And this is alpha of 2.
What,
So, yeah.
What is alpha?
Oh,
What does it mean?
sorry, alpha of 1 and 2, yeah. Sorry, that's the density cusp profile.
Okay.
Yeah. So we tried both flatter and steeper density profiles just to see the effect. And kind of unsurprisingly, you get a lot more of these repeated TDEs if you have a steeper profile and you're starting with more stars at smaller radii. So it's possible that this effect wouldn't be super noticeable if you had it's likely this effect wouldn't be super noticeable if you had shallower profiles, but when alpha is 2, so nothing super crazy even, then you are getting a lot of these repeated TDEs. Okay, and this plot is showing that. So we have again 1 minus the eccentricity versus the semi-major axis. This is similar to the plot I was showing before, but something to note here, she's plotting the initial stellar distribution in gray, but what she finds is that basically all of the stars that don't become tidal disruption events, that stars below this radius, are eventually moved outside of the hierarchical radius. And so they're very likely candidates for these chaotic orbital scatterings that we're not going to be able to model with this. We'd have to do n-body simulations to model that, but it's possible that a large fraction of these also become TDEs. But yeah, we just can't track them in this simulation. But what we can track are these repeated TDEs. And so if we focus here, these are tidal disruptions on at radii where the orbital time scale is, I think we chose less than 30 years here. There are all partial disruptions. You can see that because they're all lying right on that tidal disruption line cutoff. And if we plot a histogram of the orbital periods of these events, this is for 3 different supermassive black hole binary eccentricities. We find that we're able to get repeated TDEs on timescales that are comparable to these different, we don't know if these are all repeated TDEs, but to different potential candidate events. And so we've talked earlier about the Hills mechanism. So if you have the Hills mechanism plus EKL, as Elliot was talking about, then you can certainly also reach these timescales. But if you have just the Hills mechanism alone, for like solar mass stars, it's very difficult to get down to orbital periods of less than a few or 10 years. And so I'll leave you with my takeaways. Sorry for the technical issues there, and take questions. Yeah.
Well, first of all, I was a little confused by the term. By repeated TDE, I had originally thought you just meant the TDE rate was so high that you had multiple TDEs for a particular same supermassive black hole. Do you mean instead a partial TDE with the short enough period that you're getting.
Yeah, should have clarified that. Yeah, that's what I mean.
That's what you mean by TDE, okay.
Yeah. So previously, people have, just for general context, have predicted that one of the signatures of this process around the more massive black hole is that you might get multiple tidal disruptions from different stars. That's not what we're saying. We're saying that this process around the smaller black hole actually does repeated disruptions of the same star.
And so it is, as we talked before, I mean, there's if you think about penetration factor, whatever, there's a huge, you get full disruptions above a certain thing, and there's a fairly narrowish range between not being disrupted and full disruptions. Is there something, maybe I missed it in this mechanism that favors that narrow range?
So yeah, that's a more detailed question we might want to talk more about later, but yeah, so it basically, the delta eccentricity between the different pericenter passages will determine whether or not you get a full disruption or a partial disruption in this case. And that varies based on the radius of the effect on the pericenter radius varies dependent on the radius of the star. And so what we're finding is that at larger radii, you are getting a lot of full disruptions. It's possible you'd actually get more full disruptions than you would expect from just two-body relaxation, so more than beta the -1. But at these partial disruptions, it seems like the changes in the eccentricity on the polar orbit basis are small enough that you wouldn't necessarily expect disruption. And I think actually you would we should do some n-body simulations of that to make sure that there aren't like extra. So these are these simulations are done with the secular approximation. So we're not capturing the little wiggles that you might get on top of the sort of overall eccentricity distribution, which might slightly change the eccentricity in that final passage. But really what it seems is they're just, the change is so small per orbit that you just get the most grazing of encounter.
And just one, I guess, final question, I don't mean to monopolize the time. I think it's kind of partly shown in the middle plot here, that if you think of the standard kind of steady state, single picture, there's a mild slope, but it favors smaller black holes because the bigger black holes have emptier loss cones. Whereas it makes sense if you've got these binarity is refilling your loss cone, as you see with your blue things there, it's very much increasing with black hole mass.
Yeah.
And I guess the question is, is that, observationally, I think we don't necessarily see that, we're dominated by the largest black holes. Could you interpret that as kind of an upper bound on binarity or fraction of binaries or things?
I think that's a very interesting question. I think that you could. So I wanted originally to try to do some like more larger scale rates, but then I was discouraged when I was reading the disagreement in the literature about like hardening timescales, and I didn't want to like make any assumptions. But maybe this would be a way to kind of flip that around and just say, okay, without any assumptions, what do we expect binary to be? I think that'd be really interesting. Yeah.
I sorry, I have a very naive question. I'm no expert, but can you say again why the two-body suppression of the Kozai oscillations will lead to repeating TDEs?
Oh, okay.
Obviously.
Yeah, no. So it's
Sorry.
not that the suppression will necessarily lead to it. The suppression will lead to these longer lived rates because you're not immediately getting, so a star that is
Okay,
initially
that
starting.
makes sense.
Yeah.
Okay.
Yeah.
Okay, question. So when you added the two-body relaxation,
Mhm.
what you envision is having a sea of identical stars. My question would be, if I just were to, what would be the effect of having a population of, heavier objects like black holes that are also close to the
Right.
increase or decrease?
So yeah, we did choose but each kick is like a sort of randomized, but within sort of the kick size that you'd expect more from a population of stars. If you had a population of black holes, my initial assumption is just you kind of puff up the stars, right? Because just mass segregation. So that it's possible that would decrease the number of repeated TDEs. I don't think it would affect the overall rate. But yeah, I haven't done that calculation.
Because I have people look at the effect of having a binary in memories for compact objects.
When you say binary, you mean binary? Oh, yeah, memories. Yeah, okay. Yeah, so yeah, that's a good point. So people have done that, and so Smar has also actually worked on that and found that she can increase the rates of memories. And so that's obviously the opposite mass ratio. And so, but I still feel like I would need to do the calculation to know for sure for the opposite mass ratio effect.
Are these events gonna, like observationally, are there gonna be any other signatures other than repeating this?
Oh, well, I mean.
So like, instead of having to wait, say a year or something, and say, oh, this is.
So I do think that if we can constrain the black hole mass within an order of magnitude, then we'll see for the smaller black holes, I think it's likely that we'll see a much shorter disruption than we would expect. And an important point here is that you can also get that with a repeated TDE, but the repeated TDE timescale then you would get is then I think generally like shorter than a year. So if you don't see if you see a pretty short timescale TDE from what seems to be a much larger black hole and it doesn't repeat within a year or so, then it's I think it's a very good candidate for this supermassive black hole binary.
It doesn't repeat.
Sorry, yeah. So if you have a repeated event, yes, there's kind of two parts here. I wasn't assuming that we'd necessarily find supermassive black hole binaries from repeated TDEs. I think this is an interesting mechanism for creating them because you're still dominated in this process as you saw, I think one of the plots, you have way more disruptions from single black holes, or you have way more single disruptions than you have repeated TDEs on human timescales. But if you do see a disruption that isn't a repeated TDE and it's a much shorter timescale light curve, then that's a really good indication that it might not be the black hole mass that you think it is.
That could also be a partial TDE.
Not so yes, that changes it a little bit, but not nearly as dramatically. I can show you some papers like the timescale is the black hole mass is by far the dominant effect on the timescale. It's true that the slope of the light curve will change a bit from partial disruption, but the overall kind of shift.
Okay, yeah, see you later. Because my gut feeling would be like the partial TDEs would just be the imposters for these systems.
Yeah, I mean, I think we'd want. Oh, I think the timescales would be different. Yeah.
Sorry if I'm missing something here about you. But, are you suggesting that the 3 repeating TDEs they have supermassive black hole binaries in them?
I'm suggesting we should look into it. I don't know that they are necessarily. It's one method for creating these where you don't have to rely on. I mean, I guess actually the Hills mechanism also relies on the EKL mechanism. So it's another way to create it with these quasi-light of oscillations. Yeah, so it might be difficult to tell those two situations apart though for repeated TDEs, unless we could get a better handle on the energetics. Like if you knew the exact, if you knew the black hole mass that you would think is there pretty well, and you have a pretty good handle on and you can actually connect the flares that you see to the mass accretion rate, which I think is maybe harder to do in repeated TDEs, then you could, for some of these events, probably separate out likely candidates for supermassive black holes and from Hills mechanism. But mostly we were just pointing to it as a potential source of these.
So for like FIK, you can go and fit your light curves and get a mass estimate, right? So does that match with the M sigma or not?
I don't know, I haven't done it yet. I should. But again, sorry. So there's more complication there with the repeated TDEs because it's not super clear to me that, for example, you'd have super prompt circularization. There's other things that can lengthen the time scale as well. I think it's a better candidate for non-repeated TDEs, but
so for FIK, the idea is it did rapidly circularize because we found these iron 2 lines.
Sorry, that it did or it didn't?
It did.
Because you see the iron 2, right, okay.
It's indication of a disk. Similar to AT.
Yeah, so yeah.
It might be a good candidate for it.
Yeah, definitely. Thank you.
Okay, perhaps we can defer further questions for the discussion. Thank you, Brenna, again.